Good morning, everyone. Hope you had a good weekend. So I figured we can get started on this. As usual, we'll start with some announcements. This past review, the day 9 online homework, I opened that up a few days before the actual Thursday that it would typically be due. And I will plan to do the same thing for future reviews. Now, I should say, the next thing on here is that future exams will be cumulative, which is, you can think of it as both a blessing and a curse. In a lot of classes, I know it can be tempting to, once you've covered material, just sort of eject it from your mind. But one, that kind of defeats the point of learning the course and this, learning the material. And then two, this also gives you a chance to just reinforce what you've already learned and hopefully walk away actually remembering most of the material. I've certainly taught this class a number of times, and by the end of it, students remember nothing from the beginning, which has always shocked me a little bit. With that, you'll also have more time for review. So for example, in this next second week, or next set of 2 weeks, we'll have, Monday, Tuesday, Wednesday, Thursday, Friday, and we're on this day here. But you've got each of these days 2 weeks, and then you have exam 2. There'll be a review both on Thursday and on the Wednesday beforehand. The Wednesday will be a review of the first order topics from the first 2 weeks. And then the Thursday review will be a review of the material that we've covered during this second set of 2 weeks, or the third and fourth week. Then in the third set of 2 weeks, leading up to exam 3, you'll have 3 days of review, one for review of first order material, one for review of second and higher order linear differential equations, and then another review for the material we've covered during the 5th and 6th week. And then I think the exam 4 also has 3 days of review. I can't remember if it's 4 or 3. I think it's 3. But anyways, the number of times you review will increase as well. So it gives you a chance to look over this material more and just have more time to reflect on what you've learned. So both of these will be open on Monday for you to start looking at, the Monday of that, I guess, 4th week. So you'll see the material again, but you'll also get a chance to review it more and be tested on material that you've already seen, which in some sense should maybe make things a little easier because you're getting a chance to think about this first order material more. At the same time, I want to give students an opportunity to adjust to the course in case things weren't working out, for whatever reason. You're just kind of getting used to how the course works. So I want to discuss with the other instructor and the graders just what they think, get their feedback, but there'll be something. I don't know if it's going to be something to the effect of, dropping a lowest exam or something like this, or giving an opportunity for extra credit. I'm not quite sure yet, but there'll be something. If you didn't do as well on the first exam as you had hoped, then, don't worry about it. As long as you just keep working hard, we'll get it taken care of. And as far as what that will be exactly, I'm not quite sure yet. I mean, some students did pretty well, getting into the 90s percentages, and then there was a really wide range of scores. And I did notice that they strongly correlated with how people did on the review, which is, that part at least is kind of good, because I wanted the review, the day 9 online homework, to be representative of the exam, and it seems like it was. People who did well on that, who were prepared to do well on the review, did well on the exam. People who didn't do so well on the review didn't do so well on the exam. So it's at least representative, but I do want to give people a chance to kind of come back and still be successful in the course. But as far as what that takes, I'm not sure. I'll make a decision in the next day or two for sure and let you know. With that, you may have some questions about the material from the exam. So we certainly can go over that now. and answer whatever questions you had, or if you had something from either the homework and lab you just turned in or one of the upcoming homework and labs. And maybe this is sort of an announcement as well, but I'll remind you that the written homework 3 and the lab 3 are certainly things you can do right now. Lab 4, I believe, is also something that you can start working on right now. Like, you have everything you need. I'm not sure about written homework 4, but point being is these things are accessible at this point to you. So now I'm checking chat to see what you guys have for questions. One person asked, can you do an example of applying Picard's theorem? Sure. Let's go ahead and look at that. Yeah, Picard's theorem is a good one. So let's see a Picard's theorem example. So just a few, just like a quick restatement of Picard's theorem. Essentially, Picard's theorem says that if you have a differential equation of this form, y prime is equal to some function of x and y, and you have an initial value, if you have the following: if both f and the partial of f with respect to y are continuous on some interval that contains a, then there is a unique, let me say there exists a unique, to really emphasize the existence, and it passes through the given point. Okay. Now the key part here is you've got an if statement. If this first part is true, maybe I'll put this in, let's say, kind of a pink here, then you get this next part is true. So you have to satisfy the first part. And if you satisfy the first part, then the second part will follow. Let's look at a specific example. Suppose you have y prime is equal to 3x plus y. And you look at the point y of 1 is equal to 2. In terms of the xy plane, this function is defined everywhere. Any combination of x and y you substitute in, you'll get some sensible result. There's no undefinedness. And if you were to graph it in 3 dimensions, you could do this without already having seen it, just by graphing points. For example, if you take the point 1, 2, if x is 1 and y is 2, then 3 times 1 is 3, y is 2, so you get 5. So you'd have 1, 1, 2, and then you'd have 1, 2, 3, 4, 5. And that's one point, but there's many. However, after plotting enough of these, or if you use, let's say, an online resource, you'll find out that this is a plane. And let's see, it's going to increase like this. So I think it's going to be a plane that looks roughly like so. And actually, let me stress the perspective more. Yeah, it's not as good as I want. I want it to look like it's sort of coming out of the screen as it goes up. It's sort of coming out at you around this area. Now, the point is, if you look around 1, 2, the point 1, 2, and let me actually maybe highlight that. So let's do here. Actually, maybe let's do it here. And if you look around this point, 1, 2, 5, where the z value is 5, then you essentially just have this whole sheet around it. If you were to zoom in around this thing, what you would get is this point. And let's say you rotate it a little bit just for a better perspective, you would get kind of something like this around the point, just this little sheet area. And maybe to emphasize it a little more, imagine you had a little grid just to maybe make it easier to line up. So you'd have a little grid like this around the point. Now there's no breaks in here, just like you would have a function, let's say an orange, and you'd say it's continuous at a given point. Let's say this point, if there are essentially no breaks, it's just to use a colloquial terminology, it's kind of smooth around here and unbroken. That's our intuitive sense of what continuous means. It's the same thing in higher dimensions, where around this point, there's no like tears in the surface. There's no, jumps in points and that sort of thing. Namely, if you take a little area around the point 1, 2 in the XY plane, so the point 1, 2 might be, actually, let's put it in a different color, might be down here if it's just in the XY plane. When you get the Z value, it's this one up here. And around there, you can see that it's kind of nice and smooth. In general, if this graphing in 3 dimensions is kind of difficult, functions like this that are just polynomials in X and Y, or trig functions like cosine and sine, tangent can have some undefinedness, but if you have sine and cosine, e to the xy and things like this, these are all continuous function and multiple variables. The only time you're not going to get continuity is if you have something like a piecewise function, where maybe you have like a break in the function, where it's defined to be 0 on one interval, 1 on another, or something like this, and so on. Or if you're dividing by 0. So this function is continuous around this point. It's continuous in this intuitive way where it's sort of just this nice smooth sheet. Now you also have to check then that the partial derivative is continuous around this point. And if you take the partial derivative of this function, so this is our f of xy. So f of xy is 3x plus y. That is continuous. And it's continuous around the point 1, 2, because it's this nice smooth sheet. There's no like tears or anything. And then the other function we check is the partial of f with respect to y, and that's going to be equal to just 1. And 1 is a constant function. Constant functions are always continuous. It's continuous everywhere, so that's certainly continuous around the point 1, 2. And now if you satisfied these 2 conditions, this function is continuous, this function is continuous, and they're both continuous around the point 1, 2, then you'll have that Picard's theorem applies. In this case, it does apply then, because both these are true. So that's a specific example on Picard's theorem. Now let me check the chat and see what other people are asking about. Someone asked, on the upcoming lab, when it says lab report, what is it wanting specifically? By report, it just means a write-up of the solutions. So the report is just the sum of all the solutions. It was a term, you know, they used in that class specifically, like when they originally started writing those labs. But all that really means is just the set of your solutions that you come up with to the problems. That's all there is to it. Someone asked to go over 4.4 on the lab, and I'm going to assume that that is lab 2. Or maybe it's lab 3. So someone who asked about 4.4 in the lab, did you mean lab 2 or 3? I'll bring up lab 2. Let's see. So lab 2, we're looking at 4.4. Or I guess exercise 4. All right, exercise 4 from lab 2 is wanting to look at the equilibrium points. If you have an autonomous differential equation, so one like, in this case, using x for the dependent variable, x prime is equal to, let's say, x squared times 3 minus x. You're going to have an autonomous, or you're going to have equilibrium points wherever you have a slope of 0 and it stays 0 forever. Let's see. So we'll look at the differential equation and then the equilibrium points. Equilibrium. Now, this equilibrium points will only make sense if your differential equation is autonomous. The reason being is, since it's autonomous, you don't have any change as the independent variable changes. In this case, we'll say maybe t is the horizontal axis, x is the vertical axis. Think about looking at this differential equation and finding out where the slopes are 0. They're going to be 0 wherever this equation is 0. That happens to be when either x is 0 or when x is equal to 3. What that means is that when you look at 0, like the x value of 0, it doesn't matter what t is, you're going to have a slope of 0. And that's going to be true everywhere here. Same thing when x is equal to 3. It's always going to be slope of 0. Why we call that an equilibrium point is because if you start here, because the slopes are 0, you'll never get moved off of this path. So you have this horizontal solution. Same thing here. And moreover, all the other solutions essentially will gravitate towards or away from this. It happens to be that if we do a test value, let's say of 1, so here's 3, let's say we do 1, substitute 1 into here, we get 1 squared is 1, we get 3 minus 1, which is something positive. So you get positive values. And if we plot those, it'll look kind of something like this. And if you try a test value of 4, you'll get, let's see, 3 minus 4 is negative. So that would give you something kind of like this. Get these negative slopes, and then here I'm sure it's also going to be negative. Quick check, -1. Or no, it will also be positive actually. So you get something like this. Now, all the solutions, besides the ones that are just strictly horizontal like this, are either going to approach or be repelled by these here, these horizontal ones. Actually, let me do a little thinner there. And in some cases, like we're actually going to see here, they could be both kind of repelled and attracted to. So for the middle area, you're going to get something like this. The top area, you get something like this, and then you'll get something kind of like this. Now, depending on what these do, they'll either pull both the solutions in around them. One case could attract on one side, repel on the other side, or you could have repelling on both sides. If it's pulling in from both sides, that's stable. If it's repelling and attracting, it's semi-stable. And then if it's repelling from both sides, then it is unstable. So we have equilibrium points. X equals 0 is semi-stable. X equals 3 is stable. And so on. Then we do that for each one of these. If we have x prime is equal to 1 minus e to the x, the place where that's going to be 0 is when x is 0. The reason being is e to the 0 is going to be 1, and 1 minus 1 is 0. So x is equal to 0. And then if you substitute in, I think you're going to find, let's see, if you put negative, you'll have positive, and then, yeah, so that's going to be stable. And so on and so forth. So you're checking where this is equal to 0, and then you're just checking what happens as far as the slopes. If the slopes kind of pull in, they're negative from above and positive from below, it pulls in and it's stable. If it was, let's say, positive above and then negative below, it'd be unstable. And then if it's positive both times or negative both times, then it's semi-stable. So it gives a little idea how that one would work. Let me check the chat and we'll do one more question. Okay, someone also asked about slope fields and how you might match them up. And my suggestion is using null clines. For example, we'll do a quick match question. Since we're already talking about slope fields, say you had the following slope field. And let's say you had slopes like this. This is going to be very rough just for the sake of getting something drawn quickly here. And then let's say you had several slope fields. Say you had y prime is equal to cosine of y. You have y prime is equal to cosine of x. You have y prime is equal to x times y. You have y prime is equal to x squared minus y squared. You have y prime is equal to 3x plus y. So what I recommend always is looking at the null clines. If you look at the null clines, and I say null clines, one, because there's more than one equation, but then also because you can have more than one like null cline curve. So if we look at those, well, thinking about where this is going to be equal to 0, cosine namely is going to be equal to 0. you have things like y is equal to pi over 2, 3 pi over 2, and many other places. Just going down the list here, you have x is equal to pi over 2, 3 pi over 2, and so on. Here you have that x is equal to 0 and y is equal to 0. Both places you'll have a null-cline. In this case, with the fourth one, you'll have where absolute value of x is equal to absolute value of y, or in other words, where y is equal to plus or minus x. Those are really saying the same thing. And then finally, you have, let's see, where y is equal to negative 3x. And you get these just by setting each one of these equal to 0. Now, if you look at what these null-clines should be, in the first case, you have it where y is equal to pi over 2. Everywhere there, you should have a null-cline. That might look something like this over here. But we see that there are places where the null-cline does not match up with the slopes. So it cannot be this first one. So this one is out. Same thing with this case, when x is pi over 2 might look something, actually let me remove that. X is pi over 2 might look something like that. And we see that it doesn't match up here, here, and here. So that one is out, the null-clines don't match. This one didn't match, this one didn't match. For the third one, x is equal to 0, that would be this whole line, but we have places where it doesn't match, so that doesn't work. With the fifth one, we have the line y equals negative 3x. That would be something like this. But we see that doesn't match because it doesn't have this part at least, even if it did go along this line. So that one's out. And if you check this one, it does have the right null-clines. So by elimination, it's the only one left that could be. If you weren't sure it was at least one of them, you could do further checks and you'd find out when y is greater than x, that happens in this area, then you'll get negative slopes. And when x is greater than y in absolute value, that happens over here and here, you'll get positive slopes and so on. But null-clines is the first one I would check. That leaves this one here. Okay, with that, let's get into the material. And thank you for all your questions, by the way. I'm happy to answer them. Hopefully those explanations were helpful. Now, we talked about Picard's theorem, and I'm glad we did, because now we'll have a version of that. It'll actually be a little bit easier, in my opinion, to work with. Now, suppose you have functions p, q, f, and they're continuous functions on some interval. And moreover, what are we looking at here? We're going to be looking at a second-order differential equation. And the functions we look at, they're not multivariable functions. So it's actually even easier to work with. All we're doing is looking at single variable functions. And those are things that we are a little more familiar with because that's what we saw in Calc 1. Now, we've written this second-order differential equation. It's linear. This is important. So this is a second-order existence and uniqueness for second-order linear. And we've written it so that we have this p function here, which is a function of x, this q function here, just a function of x, f function here is a function of x. If you look back over what it means to be linear, this is what we're talking about. And let me really stress, we're talking about linear, and that's going to be the main focus of this 2 weeks. We're going to be looking at second-order differential equations that are linear. We're going to sometimes be looking at higher order than, higher than 2, but they're also going to be linear in that case. And linear is going to be the big focus for the rest of the course. It won't be absolutely everything we do, but it'll be a big chunk of what we do. So linear is really important. If you're feeling a little rusty what it means to be linear, certainly go over that and double check or ask questions and we can We can talk about it here and there. But linear is by far the big focus for the rest of the course. This is second order linear. So if you have second order linear, then you have this theorem that would apply. Now, you've got these functions, namely f, q, and p. And these are the functions that we want to check whether they are continuous or not. So let me put that in, let's say, green. So we're looking at PQF. They're the functions that make up the second order linear form here. And the other thing that we have is this set of points. And maybe let me put those in, I don't know, kind of a pink here. And then finally, the other big part that we're looking at is this interval I. Maybe I'll color that blue or cyan. Right, so what the big things to look at are the functions PQF, those need to be continuous. And they're not just necessarily continuous everywhere over the whole real line. That's not what we're checking. What we're checking is that they're continuous on some interval I. And then we're looking at a interval I, and then we're checking 2 points on that interval, AB and then, or AB naught and then AB1. And we're checking simply whether these functions are continuous, and that's really it. Let's right away look at an example. Here we have a second order differential equation along with initial value information here. Flipping back to the theorem, this says that P, Q, and F should be continuous on an interval, and that interval should contain A. The A in this case is equal to 1. So our A is equal to 1. And we want to look at an interval containing 1. If we draw a number line, and this is a set of real numbers, we plot the point A is equal to 1. Here is 0, let's say. We can pick any interval we want. Now, let's say, for instance, I pick the following interval, and then I'm going to ask you a question. Say I pick the interval going from -1/2 up to 3/2. If we look at that interval, look at all the x values in here, so we call this interval our I, is it true that each one of these functions is continuous on that whole interval? So think about, is 2x continuous on the whole interval from -1/2 to 3/2? Is e to the x is 1 over x? So would you just say in chat whether you think it is or isn't? And right or wrong, I don't really care at this point. I'm just trying to see what you guys think, kind of where you're at. And if you think it is, you can maybe give a little justification. If you think it isn't, why not? So we're checking whether each one of these functions is continuous on this interval. We want it to be that all of them are continuous there. Is that true or is that not true? I'll give you a second to type in chat if you haven't already. Okay, for those of you who typed in chat, thank you. If we look at 2x, that's continuous everywhere, the whole real line. There's no place where it's not continuous. I mean, if you just graph that function, just y is equal to 2x, let's say, that function itself is going to look something like this. It's going to look, let's see, kind of like that. It's continuous over the whole real line. That's y equals 2 to the x. Then if you look at the function e to the x, that's also continuous over the whole real line. That would look something like this. The only one where there could possibly be a problem is 1 over x. And if we look at 1 over x, that's going to be what, something like this and like so. The only place where 1 over x is not defined, and some of you pointed this out, but if you miss this place where it could be discontinuous, it's really easy to miss, so it makes sense. But it is discontinuous at x is equal to 0 because it's undefined there. This 0 is included in the interval. That means this interval of I is not a good interval to pick. However, there could be an interval. And again, just to help give you the practice, can you think of an interval, and again, type it in chat, such that all these functions would be continuous on that interval? This one we picked is not a good one for the reasons we mentioned. So can you think of one that is? And if you can think of it, go ahead and type it in chat. See if you guys are kind of getting the idea. So what's an interval that contains 1 and all the functions are continuous on that interval? And the whole reason we're doing this is so that we can try to see if this theorem of existence and uniqueness for second order linear differential equations, to see if it can apply. If we can come up with an interval like I'm mentioning here that contains 1 and all these functions are continuous on it, then we'll have a solution, a unique solution. And let me get rid of this since we said it wasn't good. And now I see some good suggestions in chat. Let me just pick one. Seems like it'll work. Let's go, say 0 to 3/2, for instance. If we go from 0 up to 3/2, and there are many that would work, but here's one that would work. If you look on the interval 0 to 3/2 where you don't include 0, but you do include 1, which we have in this interval, and we look at just, let's say over here, going from 0 to 3/2, and maybe here is 1. I know the scale's a little off, but just for the idea. If we focus on that and actually kind of get rid of everything else, then certainly on that interval, they're all continuous because we're, again, excluding 0. That means there is some interval where we can get these all to be continuous. And now what the existence and uniqueness theorem says is that there is some solution to this satisfying this information, and it's over this interval. So the actual solution is going to be something, maybe I'll put it in orange. I don't know exactly. And I hesitate to even draw, so I'm just going to draw it quick and know that I am not sure at all offhand what the solution is. But it means just over this interval, you're going to have something. So I'm just kind of drawing a little bit of a curve over that interval. That's what the existence and uniqueness theorem says, is that there's exactly 1, and actually I should maybe draw it actually like this because it does go through the 0.11. But there exists a solution, that's the existence, and it's unique. There's not more than 1. There's at least 1, there's not more than 1. So the theorem does apply. Let's look at a place where it does not apply. Here, the function u of t minus 2 is something that we'll see when we look at Laplace transforms in the 5th and 6th week. But a really quick introduction is that u of t minus 2 is simply a step function, and it looks like this, where you're 0 until you get to 2, and then you jump up to 1. You don't really need to remember exactly what this is about. We'll see it more in the 5th and 6th week. But just as a early introduction, here's what it looks like. and this value here is 2. So it's 0, and then it jumps up to 1 at 2. Looking back at the previous problem, someone asked, does it matter how big or small the interval we pick is? Nope. So I'm going to flip back. It doesn't matter at all. You could have picked a interval of, let's say, 1/2 up to 5/4, something like that. That would be a perfectly valid interval. It just matters that there is some interval. You could have even picked, I think, 0 to infinity, someone suggests that would work. Yeah, lots of them. Okay, in this case, we have this function u of t minus 2. So this is like y is equal to u t minus 2. It's just a particular function we'll happen to see later anyways, but it's piecewise continuous. It has this jump. Or it's piecewise defined. It has this discontinuity, this jump. And now if we try to look at any interval around 2, what we're going to find is any interval around 2 that we pick, it's not going to be continuous there. It's impossible to pick. No matter how small we pick it to be, how close we get to 2, any interval is going to have this discontinuity contained in it, namely right here. So the second order existence uniqueness theorem would not apply to this because there's no interval you can come up with such that this will be continuous on that interval. These will be continuous, but this one would fail to be. So it does not apply here. All right, now with that, let's look at this next concept. Since we are now looking at second order differential equations and then higher order differential equations, this notion of superposition comes into play. Let's suppose we have a solution to a differential equation that's second order. And we'll work with a particular form to begin with, let's say of the form y double prime, just like we had. But now, one caveat, we're going to let f of x be equal to 0. So if we have a solution, namely, actually, let's even call this y1. Suppose y1 is the solution to this differential equation of the form like so. And y2 is also a solution. If that's the case, you have two different solutions. You have a y1 and a y2. If they're both solutions to this differential equation, then you can take the combination of the two, linear combination, some c1, which is just a constant. Actually, it's a parameter. It could stand for really any constant. If you take c1 times y1 plus c2 times y2, this thing is also a solution. So if you have two different solutions, you can combine the two and get another solution. And in general, what you want to think is when we're looking at differential equations like this, whatever the order is, that's how many quote unquote different solutions there should be. So if it's third order, there should be 3. If it's second order, there should be 2. If it's 10th order, there should be 10 of them. I said quote unquote different, and what I mean by different is the following. We want solutions to be what's called linearly independent. So the theorem here says that if you have, again, the second order differential equation, it happens to be linear and what's called homogeneous. Homogeneous because this over here is 0. Let's actually just give a reminder that this is second order. Highest derivative is 2. It's linear and it's homogeneous. the being equal to 0 makes it homogeneous. If you have the second order differential equation that's linear and homogeneous, you've got that these two functions are continuous, and of course 0 is continuous everywhere. But if P and Q are at least continuous, you have two different solutions, y1, y2, where different, I mean linearly independent. Then it's the case that every solution looks exactly like this. So before we just said if you had two things, you could combine the two and get another solution, two solutions, combine them to get another one. But now what we're saying is if they're linearly independent, every solution can be written in this form. Every single one of them is going to look like this. So that's a little bit different. That's a more powerful statement. It's saying you can't get a solution that doesn't look like these two. So as long as you know what these two are, these two solutions, and that they're linearly independent, you know what all the possible solutions could be. Now, what linearly independent means is essentially you can't get one from the other. You can't multiply one to get the other. In a more general sense, if you have 3 or 4 or 5 functions and you want to determine that they're linearly independent, essentially what that means is that you cannot get one by combining together the others in the intuitive sense. As a really quick example, just to give you some grounding, if you look at the functions 3x and 6x, and now I'll ask a question that will get at linear independence before we formally define it. And this should be a simple question. Don't think too hard about it. Can you multiply one of these functions by something to get the other? And if you can just say in chat what you think. Can you multiply one of these by some number and get the other one? And I mean it to be a relatively straightforward question. So can you multiply 3x by something to get 6x? Can you multiply 6x by something to get 3x and so on? Okay, good. Yeah, you guys are seeing that you can. That means that these are not linearly independent. You can multiply 3x by 2 to get 6x. You can multiply 6x by half to get 3x, either way. But they're essentially the same function. Also, if you look at the function just x is also really the same as these in the sense that you can multiply x to get either one of these. So they're really all the same. They're just x multiplied by some number. However, if you take the following, let's say you take cosine of x, and then you take, let's say, x itself, or maybe, I don't know, x squared. It is not true that these, one can be multiplied to get the other. You can have these two be equal in some cases. These are equal when x is equal to, actually, are they ever equal? Yeah, they're equal at some point because they'll cross, but I'm not sure what that is offhand. You have x squared, which looks like this. And then you have cosine, which looks like this. So at some point they're equal. Actually, twice they're equal at least. But they're not always equal, and you can't multiply one by the other to get, or you can't multiply one by a number to get the other. So I'm claiming that these, without saying more formally right this second, I'm claiming these are linearly independent. You can't multiply one to get the other. Multiply one by, just a constant. Let's see what that means formally. So I'm guessing this was probably less clear. So let's look at the formal definition. So we say functions f1 through whatever, fn, are linearly independent if and only if, that's what the IFS means, if and only if we take A1 times f1 of x plus a2 f2 of x, etc., plus an fn of x if we set that equal to 0, then that implies that a1 is equal to a2 is equal to, etc. All these are equal, and they're all equal to 0. This is another way of saying that you can't multiply one by a number to get the other. This is the formal way to say it. If we take the cases of 3x and 6x, for instance, we'll see how this applies, showing that they can't be linearly independent. If you take 3x, let this be your function f1. Take 6x, let this be your function f2. Now the question for you is, and it's essentially a restatement of the question before and what you answered before, you're just using different notation. Can you come up with what a1 and a2 should be, such that if you have a1 being whatever number you think, a2 being whatever number you think, you'll get out 0. So can you state what a1, a2 should be in chat? And again, this is essentially what you've already done. You're just rephrasing it. And now I see someone answered that a1 and a2 can be 0. True. Could they be something besides 0? So can you come up with an a1, a2, and there's actually lots of combinations, such that you'll get this to be a true statement, but you don't have that a1, a2 are both 0. a1, a2 equals 0 certainly works, but we want to see, are there things besides them just being 0? Okay, good. I'm seeing some good responses. I'll pick one. I just saw a1 being -2 and a2 being 1. That would certainly work. So let's say we let a1 be -2, a2 be 1. If you take that combination, notice they're not all 0. So it can't be that by setting this equal to 0, like we've done here, that it forces all of these to be 0. It's possible that they can be 0, like some of you pointed out, but it's not necessary that they're 0. So the implication is not that they all have to be 0. They could be something else. That shows that it's not linearly independent. So this does not imply that these are all 0 in this case. Now let's look at a case where it does. So it's not linearly independent. In fact, if it's not linearly independent, we call it linearly dependent. So actually, let me add that here. So we have it in the video later and just for now. So I'm actually going to cut this and put it on this page. We kind of did the example here, but let's add that if a set of functions, or I'll just say if this f1, etc., up through fn are not linearly independent, we call them linearly dependent. So you're one of the two. You're either linearly independent or linearly dependent. In this first case, I'm going to flip back to the example. In this first case we looked at, these are not linearly independent. So 3x and 6x are linearly dependent. And we should say that when we're looking for linearly independent functions, all of this does stem from the idea that we're looking at a differential equation that's homogeneous. I'm going to flip back a few pages to this here. So we're looking at a linear homogeneous, in this case, second order differential equation, and we're looking for linearly independent solutions to it. This will extend to if we have a third order linear homogeneous differential equation, we want to find 3 linearly independent solutions, and so on and so forth. So it certainly relates to the idea of linear homogeneous. As far as nonlinear homogeneous, we won't look at examples of, like, we won't look at or have a theorem specifically that says, oh, okay, in such and such instances, you will have solutions or not. This is really just going to apply to linear homogeneous. And now in this case, we found that this is not linear. These two are not linearly independent. That is 3x and 6x are not linearly independent because we could come up with some A1, A2 set, some constants such that they're not all 0. In order to be linearly independent, it has to be that when you set this linear combination equal to 0, it has to be that these are all 0. Let's look at a case where it is linearly independent. I think it'll make more sense. So say we have the following. Let's do x squared and cosine of x, since we looked at those. Now we start by setting up this, what's called the linear combination. The linear combination is simply this sum, where we have x squared times some a1, and then we add to that an a2 times cosine of x. Just for your reference, this is a linear combination of these two. We start with this, and what we want to show is that the only thing A1 and A2 could be is 0. If that's going to be the case, if we can show that it's only possible for them to be 0, A1 has to be 0 and A2 has to be 0, then that will show that x squared and cosine of x are linearly independent. That did not happen in the previous one, which I'm going to flip back to, because we could come up with some A1, A2 that weren't all 0. Some of them could be 0, but it has to be that they're not all 0. Let's see if we can show here that they all do have to be 0. And if we can show that, that means they're linearly independent. Well, we could try just, cycling through all the different possibilities for A1, A2. Let A1 be 1 and A2 be 5 and so on. But I mean, there are an infinite number of things to check, so that's unreasonable. And if we think it's linearly independent, well, we can't exhaust all the possibilities. So let's try to show that they have to be both 0. How might that work? Well, if we start with this linear combination, what we can do is say this has to be true no matter what x is. So let's try different x values, see what we come up with, and see if it can help us show that A1, A2 are 0. Since this always has to be true no matter what x is, let's let x be equal to 0. If we do that, then if x is equal to 0, we've got A1 times 0 plus A2 times 1. This cosine of 0 is 1. That's equal to 0, and that means that A2 has to be equal to 0. Remember, this has to be true no matter what x is. So we can let x be anything we like, any number that's in the domain of both of these, and then see what equation we came up with. The very first equation we came up with showed that A2 has to be 0. Okay, that's not everything because we need them all to be 0. Now let's try a different x value. Let's let x be equal to 1. And again, there's flexibility. You could have chosen x equal to 7 or -2. Then you'll have a1 times 1, because 1 squared is 1. Then you have plus a2, but now we said that a2 is 0, so I'm just going to put 0 there. And cosine of 1, I don't care what cosine of 1 is exactly, because it's just being multiplied by 0. And now this shows us that a1 is equal to 0. And this is what we wanted. We wanted to start with this and show, just by substituting in some different x values, that it can only be that both a1 and a2 have to be 0. That satisfies the definition of being linearly independent. Now we have shown that x squared and cosine of x, this pair, is linearly independent. All right, that's good. We've got that. Now let's look at, I'm going to flip to the next page. Oh, well, maybe, is that it? It doesn't seem quite right. Sorry, I'm going to flip back to the beginning. Sorry for all the flipping. Oh, okay. I'm surprised by that. Let's look at one more instance of linear. Aha, that's why I got confused. I didn't rename these examples. Let's look at one more instance of linear independence, because this tends to give students a lot of trouble. So the more we can do here, the better. Let's look at another case where they're linearly independent. This, I guess, will be an extra example, example 3. Let's take about 1 and x. It certainly seems reasonable that you can't multiply 1 to get the other, and it's true that you cannot. So if we want to show these are linearly independent, we'll start out, and actually maybe let me color these. I think it's helpful to see the different colors. If we set up a1 times 1 plus a2 times x. So we always start with the linear combination, and then we see either is it possible to find an a1, a2 that aren't all 0, such that the equation is true, or is it not possible that they all have to be 0? In this case, it will be that they all have to be 0. The reason being is, again, you just check different x values. So we let x be equal to 0. That will show that a1 is equal to 0. Then once you have that, you'll let x be equal to -3. I could have picked 1, but I picked -3 just to show you that it could be something different. And now you have 0, because a1 is 0, times 1, plus a2, which we're still trying to find, times, now this is -3. Setting that equal to 0 gives us -3a2 equal to 0. And of course, that means that a2 has to be equal to 0. And that's really all there is to it. If you think it's linearly independent, you're substituting values and trying to show that they're all 0. If that somehow is not working, that may mean that there is an a1, a2 that are not all 0 that would show you that the equation holds. I'll do another example. Actually, I don't want to take time like making this look really nice. I'm just going to kind of fly through some examples. Let's look at x and x squared. And actually, let's look at a couple things. Let's maybe look at 3 of them. Okay. Up here, we have an A, B, and C. Some of them have more than 2, but it works exactly the same. Instead of having, an A1 x plus A2x squared is equal to 0, with B and C, you'd have a A1 times 3x plus A2 times x squared plus A3 times 2x plus x squared. So you had another term, but exactly the same idea. My question to you is, and just testing your intuition, which one of these do you think is linearly independent or not linearly independent? Just your intuition. I'm not expecting you to be right or wrong necessarily immediately. Just what do you think? I'm kind of looking for feedback on what your intuition is. So which sets do you think are linearly independent? Maybe you can just type, I think A, B are linearly independent or something. Okay, so thank you for the feedback. I'm getting kind of an idea what you guys are thinking, which I appreciate. If we look at the first one, I'm just going to run through these just quick, just so you see what the answers are, and then we can go into detail for some of them, how you show it is or isn't. The first one does actually happen to be linearly independent, which will be an important thing later. So let's do blue for linearly independent, red for not. And we say the word linearly both times, so let's just say independent. Cut down on the redundancy for the moment. The second one is dependent. The third one is going to be actually independent. Now, if we say it's going to be dependent, then what we need to be able to do is come up with an A1, A2, A3, showing that the linear combination is equal to 0, but not all the coefficients are equal to 0. So right here, I've got this set up. So what should A1, A2, A3 be? A1, let's let that be, actually, let's let A3 be 1. Let's let A1 be equal to negative 2/3. Then A2 should be equal to negative 1. Just looking over that really quick. Yes, that should work. Because if you substitute those in, what you'll get is negative 2x minus x squared, and then you'll get plus 2x plus x squared. Now I'm going to sneeze. I apologize. Oh, excuse me. So here are the A1, A2, A3 we came up with. Now, it doesn't have to be that they're all non-zero, but at least one has to be non-zero, and certainly at least one is. Now, as far as, let's say, showing the 2 up here are linearly independent, this is a case where I think using 0 will not work. So let's set up A1 times x, and this will be the last thing we do, A2 times x squared. I'm going to do this really fast because I kind of want to get you out before actually 9:15. Let x be equal to 1. That will give you A1 plus A2 is equal to 0. If you then let x be equal to, how about negative 1, then you'll get negative A1 plus A2 is equal to 0. Now here's a case where you don't immediately have that 1 is 0. You can't immediately say, oh, A1 is equal to 0. But you can now take these two and add them together, for instance. If you add A1 to negative A1, you get 0. If you add A2 to A2, you get 2A2. add together, and you get 2a2 is equal to 0. That means a2 is equal to 0. Substitute a2 equals to 0 back here, and that will imply that you get a1 is equal to 0. You'll see the exact same thing for C. And with that, I think I'll actually end before 9:15. So you're welcome to stick around if you've got questions that you want to ask. I'll be here till 10:15-ish. Otherwise, you have a good day. It's good talking to you. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.